Good evening. My name is Reed Corbett. I'm the Executive Director here at the Coastal Studies Institute and want to thank you all for coming this evening for our first Science on the Sound of 2024. I am very excited to see several of our students that are in the audience tonight that are here for this semester, so new to our community here on the Outer Banks and be spending the next 15 weeks with us. Science on the Sound is something we always try to bring to our community, introduce some of the scientists that we work with directly, some scientists that we collaborate with, maybe outside of our own organization. An opportunity to learn a little bit about the work that we are doing, and I say we fairly broadly. We are doing usually coastal focused, but likely very interested, for our community. And so thank you for coming this evening. I heard somebody say there was another presentation on wind turbines at Duck that we're competing with. So anyway, we got a full room, so thanks for seeking us out. And there's a lot of other things that we do offer that I encourage you to get on our website. There's a sign-up form over, I think there's a sign-up form on that table over there that if you want to put your email address and get on our, we don't send a lot of emails out, but we do have activities at CSI. We try to send out an email to our list so people are aware. A date to put on your calendar would be April 20th, which will be our open house. And so we open up our campus, we have a lot of our scientists, all of our rooms, our labs are available for you to sort of peruse, learn a little bit about the research that we're doing here, a lot about some of the other programming, both K-12 as well as adult learner programs that we have, see some of the vessels and other equipment that we use to do our research. And so I encourage you to sort of join us, let your friends, neighbors know, April 20th, Saturday. It's usually like 10 to 2, don't hold me to that yet. We'll be getting some marketing information out on that soon, just thought I'd give you a heads up. And one other thing I wanted to announce is our next Science on the Sound. And so we are trying and do have science events like this, Science on the Sound, every third Thursday at 6 p.m. each month. I think that makes sense. For the spring. We are certainly running through May. And the next one will be February 15th, Life in the Salt Marsh Underground. Dr. James Ferry, who's a faculty emeritus at Pennsylvania State University in the Department of Biochemistry and Molecular Biology. So that'll be February 15th. Okay, so those are my announcements. I'm very happy to introduce Dr. Rosana Ferreira. I can't roll my R's, who is a professor in the Department of Geography, Planning, and the Environment at East Carolina University. Dr. Ferreira, again, I can't roll my R's. You can do it better. You'll introduce yourself rolling your R's. Hails from Sao Paulo, Brazil, where she did a couple of degrees in meteorology before going to Colorado State University for a Ph.D. in atmospheric science, and has been at ECU since I think 2007. And recently sort of joined our organization as the director of our Ph.D. program, which is Integrated Coastal Sciences. And she's here to talk about some of the work that she does, sort of studying regional climate dynamics. So, Rosana, thank you.
Thank you. Thank you, Reed. It is on. Thank you very much. Thank you all for being here on a cold evening like this one. I know that being from São Paulo, in the tropics, subtropics, I would probably have had a hard time getting out of the house in this cold. Back then, now after I lived in Colorado for 7 years, I'm okay. So I am going to talk about climate change, science, prediction, and climate extremes. And just a little bit about me. As Dr. Corbett said in his introduction, I am originally from São Paulo, Brazil. So I went to the University of São Paulo, then Colorado State University. I spent a few years at NASA Goddard, which is just outside Washington, D.C., in Greenbelt, studying climate, using climate models to study climate, mostly current climate and past climate. And my work has been funded by the National Science Foundation, NOAA, and also NASA over the years. Some of my research interests are to combine observations and numerical models of the atmosphere to understand climate variability and dynamics. In particular, I have studied African easterly waves and tropical cyclones in the Atlantic and in the Pacific Oceans. I have studied the South American and African monsoon and mid-latitude cyclones. I'll talk about those a little bit today. And also precipitation in the southeast United States. And more recently, asking the question, as the tropics expand, as our climate warms and the tropics expand, is there a possibility that the southeast United States will become more of a monsoon climate, which currently it is not. I wanted to just establish a baseline here. I really like this picture here, and it shows sort of the difference between weather and climate. Weather is what happens on a day-to-day, hour-to-hour basis, and it's sort of like this dog here going, which in every way, and climate is sort of the average of the weather. So climate is regulated by global forces, such as details of the Earth's orbit around the sun on very long time scales, like hundreds of thousands of years, for example. It's also regulated by the amount of solar energy received and reflected by the Earth, very much regulated by the distribution of land, oceans, and ice, and it's a two-way interaction. The climate affects the distribution of ice, for example, and the ice affects the climate back. And it's also based, very much dependent on the composition of the Earth's atmosphere and on the fact that the atmosphere has, that the Earth has an atmosphere also, of course. So the climate keeps the weather on a leash. Here's a little bit about the composition of the atmosphere. Most of the atmosphere is nitrogen, 78%, oxygen at 21%, and carbon dioxide and these other gases are a much, much smaller percentage of the composition of the atmosphere. However, a very important part of the composition of the atmosphere, because carbon dioxide, water vapor, methane are gases that are greenhouse gases, which means that they absorb certain parts of the radiation spectrum in the infrared that allow the atmosphere to warm up. So this is kind of a figure that we don't really need to go over in detail, but it just shows what portions of the radiative spectrum gases in the atmosphere absorb. And each gas absorbs a different portion of the spectrum, and that's why we say that the atmosphere is a selective absorber. So for example, the atmosphere itself doesn't absorb most of the energy coming in from the sun. It goes right through it. As you can see, that not much is absorbed here in the visible part of the spectrum. It does absorb infrared radiation, which is mostly emitted by the surface of the Earth. So the energy comes right in, comes in from the sun, it's absorbed by the surface of the Earth, and it's emitted back out as infrared radiation. So it comes in as solar radiation, and it goes out as infrared radiation. And if there was no atmosphere on our planet, the equilibrium between what's coming in and what's going out would produce a much lower temperature than the temperature that we see, than we enjoy right now. So it would be about 0 degrees Fahrenheit on average on the surface of our planet. But it is much warmer than that. And that is because you have this solar energy coming in, it's absorbed at the surface, and it's emitted back out, but some of that infrared then is absorbed by the atmosphere. Gases like carbon dioxide, water vapor, methane are absorbing this infrared radiation coming up, And that's like putting a blanket on the Earth. And so the average temperature ends up being a lot warmer. About 60 degrees Fahrenheit is the average temperature of the surface of the Earth, temperature at the surface. So much better. And that is because of this greenhouse effect. And so it stands to reason that if you add these greenhouse gases to the atmosphere, the temperature would increase. And that is just, you know, you can in fact do an experiment in a couple of bottles of air. You just can see the temperature change if you heat them up with infrared radiation and you have air in one of them and no greenhouse gases in one of them and not in the other one. You can just watch it warm up. So there is a trend that has been observed since the 1960s at the Mauna Loa Observatory in Hawaii. This is an observatory that has been measuring carbon dioxide in the concentration in the atmosphere since the late 50s. And this curve, it has an exponential growth, like what you see here. In fact, I wasn't keeping track of it, and I was a little bit surprised the other day when I updated some of the slides in this talk, and it used to be a 400 here just in 2017. It was the latest measurement. And now we are at 422, and it was a big deal when it crossed 400. So it keeps going up. So there is a trend here. There is also this up and down, and that's the annual cycle. And I think that's really cool because what you're seeing here is this curve, the annual cycle is basically following vegetation in the northern hemisphere, because you have deciduous vegetation in the mid-latitudes in the northern hemisphere, mostly ocean in the southern hemisphere. And so what's happening is these trees are growing leaves in the spring, and so they're taking carbon out of the atmosphere to grow the leaves. And then in the fall, the leaves fall, and the carbon is put back in the atmosphere. And so you see these up, down, up, down, up, down. That's the annual cycle. I think it's pretty cool because it looks like you're watching the atmosphere breathe or something, right? Because the northern hemisphere trees are producing this signal that you can watch, that you can measure in the middle of the ocean in Hawaii, right? Because carbon dioxide is pretty well mixed in the atmosphere. So I just think this is really cool. This is then carbon dioxide concentration going further back, and this is, you can see the CO2 concentration going up. The record that I showed you is the directly measured record from late 1950s on. This older record here is data that you get from ice cores, probably. I'll talk a little bit more about ice cores in a little bit. But what you see here is the change in global temperature also. So we had cooler temperatures and or negative temperature anomalies. So it's just, it's the global temperature compared to a certain average, to the mean value in this figure. So you average all of them, and then for each year you subtract the average and you get an anomaly. So you can see that the temperatures have been increasing gradually as the CO2 concentration increases. And that makes sense based on what we know about the chemistry of the atmosphere and the physics of how radiation interacts with the atmosphere. So if you want to go further back into the past, that's also possible because the atmosphere saves tiny bubbles of air as snow falls in Greenland, for example, or in Antarctica. You have very deep snow that has been saved for thousands, hundreds of thousands of years. And you can go out there and drill a core into the ice and then look at burst the bubbles in a vacuum chamber and measure what gases are in there. And so we can have an estimate of what carbon dioxide concentration was going past past 800,000 years. And so you can just see here. This is from 1958 on. You can see that this is that stretch of the curve that I was showing you before. And this is for the past 800,000 years, what was measured in an ice core. I believe this is the Vostok ice core. And someone can correct me if I'm wrong, but I think it is in Antarctica. But it's well mixed, so it's a good proxy for what carbon dioxide was everywhere. But anyways, the important point in this figure here is that you just see that the carbon dioxide concentration, at least for the past 800,000 years, has not been anywhere near what we find now. And this continues to increase. Oh, it's the Vostok ice core in Antarctica. And this is just a 400,000 year period from the Vostok ice core. You can also get an estimate of temperature from these ice cores because you can also measure the concentration of different isotopes of oxygen, and that gives you a thermometer that you can use to kind of estimate what the temperature was when back in the past. So this is thousands of years before present, and you see that the temperature follows the carbon dioxide pretty well. So then the question is, many times, is the extra CO2 that is in the atmosphere because of us? And again, you can look at the concentrations of different isotopes of carbon. And we have a really good indication that the increases in carbon dioxide in the atmosphere are due to fossil fuel burning. And like you can say maybe it's volcanoes, but volcanoes release a different kind of carbon, carbon-14. The fossil fuels will release more of carbon-12. And therefore, what we see here is a decrease in the relative amount of C13 to C12, which indicates that we are burning a whole bunch of fossil fuels that increases C12, and you see a decrease in the relative amount of C13. So the chemical signature of these ice cores is telling us that the carbon dioxide increase in the atmosphere that we are seeing now is due to the burning of fossil fuels. And then this is a long time series going back to 1850 of temperature of the mean global land and ocean temperature for the whole year. And this goes back to 1850. And you can see here that the temperature has, from the beginning of the time series to now, the temperature has increased. These are temperature anomalies again. There was a period here when the temperature kind of stopped increasing for a while, and then it picked back up again. And you can see here, 2023 is the warmest year on record. Another thing that I would like to point out is that the temperature increases are more significant over land than over the ocean. Land heats up and cools down faster than water does. We have a large increase in temperature in 2023. You can see also that the temperature anomalies are positive pretty much everywhere on Earth. So we're seeing an increase in the temperature of over land, about 3.2 degrees Fahrenheit from the 1800s. Last year was 1.5 degrees Fahrenheit warmer in North Carolina, but if you look up here in the Arctic, some portions of the Arctic have had increases of up to 9 degrees Fahrenheit, which is a large increase in temperature. You will hear a lot, we hear a lot about how this past year there was a strong El Nino out in the Pacific Ocean. And what that means is basically you have a change in, you have a lot of warm water switching to the East Pacific from the West Pacific, and it's water coming in from the deep in the West Pacific, and it just surfaces all as really warm water in the Eastern Pacific. And that changes many patterns of weather all over the world, especially in the tropics. But it also heats up the atmosphere because you're bringing all that water up, all that warm water up, which you can see here. And it's interesting in this figure here, I just put El Nino happens every 3 to 7 years or so. And I just put in here the strongest ones that have happened in this time series. And there was the 72, 73, and you see there was a big jump in the mean temperature globally. And then there was the 1982-83 El Nino. There was also an increase. And then 97, 98, there was a jump. But so you have this trend. 2015, 2016 is another big one. And now we have the 2023, 2024, which is also a very strong El Nino event. But what you see is there is these big jumps, but the whole curve is going up and up. And so these patterns of the increase in carbon dioxide and also El Nino and things that happen naturally in the atmosphere tend to produce a lot of significant weather events all over the world each year. And some of them are things that we can't pin to climate change. So for example, you can't tell Hurricane Otis or Cyclone Daniel was due to climate change. It's hard to make that attribution to an event. But other things are just easier for us to pin onto climate change, such as changes in the Arctic sea ice extent, or the fact that North America had its warmest year on record, for example, or heating of the global oceans, for example. So we are seeing these slow upward trends in the global Earth system. Here's another big important thing. The Arctic sea ice extent has been decreasing. And this figure here shows you the ice edge during the summertime. And this is the yellow line here shows you what the average sea ice extent used to be. This is average from 1981 to 2010, the yellow line. And in white, you see what it was last September. And September is the warmest time of the year in the Arctic, and so it's the time when you have the least sea ice extent. And all the ice that you see that you see here is ice that is floating on water. And so you can say, well, it doesn't matter, it's floating on water. It's not going to raise sea levels, right? Because it's like you leave your Coke in a cup on the kitchen sink, and there's ice in it, and it doesn't overflow when the ice melts. It's just floating in the water. But so Antarctica has a ton of ice that could do us a lot of harm, and so does Greenland, but not the Arctic sea ice. The thing that the Arctic sea ice does is it exposes the ocean. And so what you end up having is something that we call the ice albedo feedback, or Arctic amplification. And what you see here, and it's just summarized in this picture here, as the ice melts, you have more ocean exposed, and the ocean doesn't reflect as much solar energy away from our planet. It absorbs more, which means it keeps the energy at the surface, and it warms the ocean, which leads to more ice melting and further warming up of the Arctic. So this is an important part of so even though it's not going to create any sea level rise, it's going to warm the whole system up. And it might contribute to melting in Greenland, for example, which will be a problem. If all of Greenland melts, then we have about 18 feet of sea level rise globally. And Antarctica is a whole other story. You could have about 180 feet. Now, it will take a long time to melt that much ice. So, but there are things hidden, there are secrets in the ice there, that there's physics in the ice that we still don't understand, and kind of surprises that sometimes come up, and scientists discover something that usually work against us. Usually it's like, not that it's going to melt slower, usually it's going to melt faster. So, so the global average sea level rise has risen about 8 to 9 inches since 1880. And then this is like what has happened in the past, what's going to happen in the future. And so how can we make predictions for what's going to happen in the future? These predictions have been made since the 1970s. What the tool we use to make these predictions is basically the same tools we use to make weather forecasts, only we apply it to climate. And so for weather, we take these high-resolution numerical models of the atmosphere, and we run them out for 10 days. And we run it, because the weather is chaotic, we have to run it many times to get sort of an average of what might happen in the next 10 days. And you can ask the question, yeah, if we can't even forecast the weather, how are we going to forecast climate, right? And the reason for that is we're asking very different questions. So with weather, I want to know if it's going to be warmer than today here in Manteo on Sunday. The answer is not. But that's because of a weather forecast. But with climate, all I can get to is a very different question. Is it going to be colder than usual here in North Carolina next winter, for example, or this summer? So it's a different kind of question that you need when you're talking about climate. And answering these questions are usually some things that help businesses plan for what they're going to stock in their shelves, or how many people are going to visit their towns, and so on and so forth. So it is still helpful. And climate is anchored by what's happening in, say, the ocean. For example, when an El Niño event is out in the Pacific Ocean, we can expect certain shifts in the climate, and so we can use those shifts to create climate forecasts. And also ice and land surface processes allow us to run these models then for months to a century. These climate prediction models are mathematical representations of these equations here. So I like to show this because it looks like a black box, but it is not a black box. We know what the physics is, sphere, and we translate the physics into mathematical equations, and then we write the mathematical equations into a computer code. And then we use observations from the real world atmosphere, and we use those observations to start the model and run it into the future. And so I can just give you a little tour, because I am a dynamic meteorologist and I absolutely love these equations. But I can say, so I can say something like, for example, here comes, let's say you can put the sun in here, and that's that Q there. So I heat some portions of the Earth's atmosphere, say the tropics more than the exotropics, and that will cause a change in temperature. And that change in temperature, if you go over here, that's the T, is going to cause changes in pressure. And differences in pressure, as you see here, this delta P over delta X, that's a change in pressure with respect to the east-west direction, produces a wind, which is this U here. And then the wind moves the warm air and cold air around, and that, it's this feedback going on and on and on. And so the F is the choreo. Oh, F, you mean this one, the big one?
Right.
Yeah, that's friction. friction with the surface or friction with mountains, for example. And so you take those equations and you write them up for each one of these grid points here, if you have a global model. And you write them up for each point, and you write them up for each level in the atmosphere. And the bigger your computer gets, the more places you can model, right? So our computers have gotten large enough that we can model the entire world, maybe at a resolution with these little squares of 10 kilometers, 20 kilometers, and more layers in the vertical, so you represent the atmosphere better. And then you use these models to make the predictions. And these models have gotten more and more complex. And as the computers get fancier, we are able to model more and more phenomena. So we started maybe just with the atmosphere, and then we added an ocean model. And then in the 80s, we started getting these coupled climate models that had sea ice in them. And as we go forward here, you can see that there is interactive vegetation. We are modeling the carbon cycle, ice sheet dynamics, atmospheric chemistry, and we just keep making them fancier and fancier and fancier. And now this is the part where I would be like, where I have to tell you that there's a new kid on the block now, which is AI. And AI, there is a great podcast in Science Magazine that talks about how AI is revolutionizing weather forecasting, but not climate forecasting yet. So my beloved equations, like just being like, I don't know, corrupted with AI. No, not corrupted, absolutely like bypassed and neglected. I can't stand it. I can't stand this. So there's something called, there are centers all over the world doing these forecasts, and then everybody starts comparing their model forecasts to the other ones. And these forecasts are done for so many countries, and these guys are doing thousands of years of simulations collectively. And what you can see, and I'm going to skip that one because this kind of this has the same information. So this is the observed temperature of the planet. And these runs were done at the NASA Goddard Institute for Space Studies, so NASA GISS. And just the figures were made for a magazine here. But you can see the temperature has increased since 1880, and these are to 2014. And then the question here is, what is making the temperature increase? And so the scientists asked the question, is it the sun? And then they did a model simulation, or a set of model simulations, and they added solar variability to the simulation. And you can see here it's the orange line, and the orange line shows that the temperature wouldn't have changed that much if just the sun was at play. Is it the Earth's orbit? Again, the same thing. The changes in the Earth's orbit take thousands of years to occur, so that couldn't be it either. Is it volcanoes? Well, volcanoes tend to have the effect of cooling down the atmosphere. You can see the big volcanic eruptions there. So not that. So could it be all three things combined? No. Natural factors like the ones are not what's doing this. And then could it be deforestation? And you see again here that by including land use in the model, it didn't make a change. Could it be aerosols? Well, aerosols tend to cool the atmosphere. Could it be ozone pollution? And that is not enough either to explain the observed changes. And that's what's beautiful about these models. They're complex. They do a good job at representing changes that have happened in the past. if you add the right stuff into these models. And so is it greenhouse gases? And so they added greenhouse gases to the simulations, and you see that it kind of overshoots. It heats the atmosphere more than it was expected, than what actually happened. And then if you add to that everything, the human factors and the natural factors, you end up with a much better fit. And in fact, the fact that aerosols tend to decrease the temperature explains why the temperature stayed flat in the 1950s, 60s, and 70s. It was that effect of the aerosols cooling, countering the effect of the greenhouse warming. So it made it flatter. And so that was a much better fit. If you add everything in the volcanic activity in that, you can see that some of these volcanic eruptions like Mount Pinatubo in 1993, El Chichon in Mexico, and Agung in Indonesia, you can see the effect of cooling that those volcanic eruptions had. And so we have something called the IPCC, the Intergovernmental Panel on Climate Change, and they analyze all of the scientific articles that are produced on climate, and they assess human-induced climate change, impacts of climate change, and also adaptation and mitigation. And some of and initially, this is from 1990, the main takeaway message was the observed warming could be largely due to natural variability. And this is the assessment number 2, the AR2, 94, discernible human influence on global climate. So by analyzing the literature and observations and all of those model simulations, we start seeing these patterns emerge over time. By 2007, we had very high confidence that human-induced warming is leading to important changes in the climate system. And the most recent one in 2021 says that it's unequivocal that we are having an influence in the Earth's climate. And we're seeing rapid changes in the atmosphere, ocean, cryosphere, and biosphere. So the big uncertainty going forward, of course, is what we are going to do, what humans are going to do. So what they do to forecast the climate in the future is you come up with some scenarios of what you think humans might do going forward. And there's some very unlikely scenarios here, which is that we would stop putting carbon in the atmosphere altogether, or we maybe would half the amount that we put into the atmosphere going forward. And then there are these other scenarios here, which is that we would continue with business as usual, more like scenarios. And then you run the models again, and they tell you things about how the climate could change in the future. And so some of these simulations give a 4 degrees Celsius global warming by the end of the century. Right now, we're about 1 degree warming. So this is 4 times what we see now. And that land areas will heat up faster than the oceans. That's important to keep in mind. And also the Arctic and Antarctica will warm more than the tropics. And that has all those consequences for the oceans and sea level rise. And also the precipitation extremes. It's like the places that now get a lot of rain will get more, and the places that don't get a lot of rain will get drier. Some other predictions here. The global surface temperature will increase, like I said. Arctic sea ice, the Arctic might be ice-free in September by 2050, which is a big, a huge change that will have large consequences for atmospheric temperatures. And the global mean sea level rise, which these models, right now I think we have about 20 centimeters, 8 inches of sea level rise, but some of these models are are showing up to 1 meter of sea level rise. And we can ask the question, why does it matter? And here's a baseball analogy. More CO2 will change the playing field. It's like bringing the what is it called? The fence in 30 feet. Even I could have a home run, right? Probably not. but that's the idea. So you know, and why does it matter? It matters because extreme weather causes a lot of deaths every year. Just last year, 492 people died in the US because of extreme weather, and a lot of economic damage as well, at least 90 billion that we have tallied from severe storms and tropical cyclones, mostly tropical cyclones, which are things that affect us here in eastern North Carolina. And some of the weather extremes that affect us here are tropical cyclones like hurricanes, and also mid-latitude cyclones like those northeasters running up the coast. Here they can form over here in the Gulf of Mexico, or here, these cyclones, and just run up the coast, producing a lot of rainfall and storm surges. You have to think about the fact that the sea level is a little higher, and when the tides are higher and you have maybe a king tide, if a hurricane or a nor'easter hits, then there's going to be more storm surge and more damage. And we have more and more people living at the coast as well. And I was going to go a little bit over, you know, how a tropical cyclone forms and that kind of stuff, because I just really love all of this, so I could be here till tomorrow. But just a couple of things about how these storms might change in the future. So mid-latitude cyclones, their tracks have likely shifted poleward in both hemispheres, so they're moving a little bit further north and away from us here in North Carolina, and that's where we could have North Carolina and the southeast United States become more monsoon-like, like where I come from in Brazil. And that shift is expected to continue, that shift poleward. For tropical cyclones, which everybody is interested in, it's likely that the global proportion of major tropical cyclones has increased and will continue to increase going forward. And that's, you know, makes sense. You have a warmer climate. That's what, you know, the oceans are getting warmer, and that's what you need to intensify a hurricane. You need warm sea surface temperatures. It's also great that the jet stream is moving further north, because hurricanes don't like to be near the jet stream. So you have a confluence of things that are helping make these storms stronger. Let's see. And the precipitation coming from these systems is also going to increase, because as the atmosphere warms up, it can hold more water vapor, and then you can have more rain. These storms can also become slower propagating, and we have seen a tendency for storms to propagate more slowly. Poster child for this was Hurricane Florence in September of 2018, and as the hurricane made landfall, it propagating more slowly, and Hurricane Harvey did the same thing over Texas a few years back. And it's just like you have this bucket of water, and if the bucket continues going, it's not going to make as much of a puddle as if it stops and starts and continues pouring that water. So a lot more flooding potentially coming from these storms. And I'm going to skip some of this stuff that I really like. I'll just make the point that when I started teaching this tropical meteorology course, and I made these figures, this number, and I'll have to tell you when that was 20 years ago, this number was 10. And this number was like 5. So these numbers have gone up over the years. And this is all connected. So these hurricanes that we get here, about half of them come from Africa. And so as the African monsoon maybe intensifies, maybe we'll get more waves, African easterly waves coming out of Africa, and more potential for hurricanes out in the Atlantic Ocean. Let's see, I'm gonna skip this too. I will just mention this one, like what is that? Hitting my home down in South America. Like this one thing that the Climate Center in Brazil was not calling as a hurricane, because there are no hurricanes in the South Atlantic, right? And the people at the National Hurricane Center in Florida were saying, it walks like a duck, it quacks like a duck. It is a hurricane. And then finally, when it made landfall, it was like, oh yes, we had a hurricane. And so I talked about this, basically. Why is it going? Oh, it's going forward. I thought it was going backward. So it's very likely that heavy precipitation events will intensify. There's medium confidence that the Hadley cell has widened and it will continue to widen in the future. And my work, which I haven't talked about now, has to do with trying to understand if we will be in a more monsoon climate here in the Southeast United States, using some of those climate model simulations and even weather model simulations with regional models. And also the proportion of intense tropical cyclones and peak wind speeds are projected to increase at the global scale. And combined with sea level rise, this is a real problem for those of us living on the coast. So impacts are, of course, weather extremes that I've been talking about. There's also impacts for human health, which changes in the range of pathogens, for example. There are ecosystem disruptions, coastal erosion, agriculture, impacts for the global economy, impacts for national security as well, with people competing for more resources that are or people migrating from the coast to other places. So a lot of very complex problems coming out of the changes in our climate. And that brings me to ICS, which is the Integrated Coastal Sciences Ph.D. program here at CSI. And those 32 current students at ICS, one of whom is sitting right there, have projects that integrate. They're trying to solve what we call these wicked problems that have so many different components to them. So we have students studying changes in fisheries, both in terms of how can we manage fisheries better and ecology, so combining different fields of expertise to try to help propose solutions for these problems going forward. So we have students studying renewable energy, and that's at the boundary of oceanography and engineering. We have students studying archaeology, and one of our students was here speaking to you last fall. Hydrogeology with a project on geology and economics, sustainable coastlines, mosquito biodiversity. Believe it or not, there are climate model-like models for mosquitoes. And how the mosquito range will change and how that will change infectious diseases, and then, pollution, climate change, water resources. So these students are out there doing great field work and great research in studying all of these cool fields. And with that pitch for the ICS PhD, I will open for questions.
So we are streaming this, and so I just ask that if you have a question, raise your hand, and I'll sort of hand you a mic so that way people online can also hear the question.
Could you explain a little more what you mean by becoming a monsoon climate here locally? I just didn't get really what details you're talking about.
Yes, so that's a very good question. What do I mean by becoming more of a monsoon? So a monsoon climate by definition is a climate in which you have a very distinct annual cycle of precipitation with a distinct minimum in the wintertime and a maximum in the summertime. So the Amazon basin, for example, is a classic, well, not classic, but it is, I consider it a classic monsoon climate. Or India has a classic monsoon climate, where you have temperature increases over the continent during the summertime. The winds blow toward the continent. That creates a rising air, which creates clouds, and you have a lot of precipitation during the summertime, say, for example, in India or over the Amazon basin. And then in the summertime, right? I'm so sorry. In the summertime, the wind blows toward the land where it's warm and rises and makes clouds and rain. And in the wintertime, the wind changes direction because the ocean becomes warmer than the land as the land cools. And then the rain goes to the ocean. And so the land stays kind of high and dry, no water. Here in eastern North Carolina, what we have is it rains all year round. It's basically flat if you look at the rainfall. However, we have a study using radar data in the southeast United States. And what we found is that if you separate the rainfall that is small scale from the rain, say less than 100 kilometers in length, so from large scale rainfall features that are, say, an entire cold front, for example, if you split them, if you separate the precipitation that's isolated small from the large scale, what we get is the isolated precipitation is following that same rhythm that the monsoon does. And so what could happen is the jet stream is moving poleward, and so the frontal systems are going to be delivering their rainfall further north and leave us here in the, say, margins of the tropics and the subtropics with a precipitation, with those small precipitation features that have an annual cycle that looks like a monsoon. Long answer. So that's using radar data for the past 10 years, that study. Yes?
My question is, so you said there are things that we do that heat up Earth and that things we do that cool down Earth. Do you think we can just like do the things that cool down Earth to lessen the effects?
So that's a very good question. What is problematic about that is, like, for example, we could dump a lot more aerosols in the atmosphere that will cool the atmosphere, but that's pollution. Part of the reason why the heating continued was that the EPA in the United States came on board, and they mandated that pollution be decreased by cars and all that. And so there's fewer aerosols in the atmosphere going forward, and so that cooling trend from aerosols may have decreased because of that. Like other things that we could do, and those things are all problematic, because I had a professor at Colorado State University who had come up with this idea that when a hurricane, just before a big hurricane hit a major US coastline, we could go out there and dump a whole bunch of oil, honestly, on the water to keep to cut off the fuel, right? Because then there's no evaporation of water up into the atmosphere, and the hurricane will just die down, right? And I remember going to an American meteorological, he actually gave that talk at the AMS meeting, American Meteorological Society meeting, and there were all these people from insurance companies in the back of the room, and it was a commotion. So anytime, and coming here today, I was hearing this other science podcast talking about how It would be like to get the oceans to absorb more carbon from the atmosphere, we would need to make the oceans less acidic. And then you would have to dump like 1 billion tons of magnesium hydrate into the ocean for that one purpose. So, you know, everything, it's all connected. Everything has a consequence. And there's bound to be people who don't like the consequence. So, you know, we should imagine all the solutions that we can. I'm all for curiosity and, you know, trying to figure out creative solutions for problems, but then you're always going to have to worry about the bad things that could come out of that.
So last year's hurricane season, at the beginning of the season, we heard like, oh, it's going to be a milder than normal hurricane season. And before it actually started, we got a completely different prediction that was like, oh boy, buckle up. And so I'm wondering, did the inputs change? Did the models change? Like what changed that prediction and so early in the season?
Right, so these hurricane season predictions for the Atlantic start, like there's already one out for this year. And they start like in January, the various centers that do that. Actually, the first center to do a seasonal prediction was at Colorado State University. The same professor that I just told you about, Bill Gray, started the first seasonal predictions for the hurricane season. He was an amazing guy, by the way. And then other centers started doing that too. So, you know, this past year, a big El Nino was brewing out in the Pacific Ocean. And just when you start seeing an El Nino start, you think there's going to be fewer hurricanes in the Atlantic Ocean because it brings the jet stream southward, and that hurricanes don't like that jet stream to be south because hurricanes like to stand up, and the jet stream with those strong winds up above, it tilts them, and that's just not good. So I think the early forecasts were based on changes on El Nino and the Southern Oscillation, but the forecasts keep getting updated actually all the way through August because the peak of the hurricane season is September, so they keep updating them and more data comes in. And it's the same models, but you just have more data, like you know how strong El Nino is going to be, what's actually out there. And I apologize, but I don't remember what made the forecast change last year, despite El Nino. This year is going to be La Nina, possibly, but it won't be full-fledged until the end of the year.
It seems a little bit of a paradox to me how we're hearing, and I think climate prediction is like the chaos theory. It's a whole paradox in itself. I mean, you put in all the variables and there's a predetermined result, but you really can't effectively predict it. So that's maybe why. But what I'm driving at is that we hear more and more about how there's the least snowfall that we've had in years, and the groundwater is disappearing. There's places that there's droughts, so they're using the groundwater for crops, and people are mad because now there's not water for people. So there's less and less water, and then this talks about increased and increased precipitation. So can you just explain that apparent paradox to me, please?
Yes, so it's going to, so that's the thing. We're using more groundwater because there's more people, more and more people also. And that's something that has to be taken into account in those models making forecasts for the future. So we're using more and more water, and it's going to rain more where it already rains. So for example, it would rain more, say, in the middle of the Pacific Ocean in a region we call the ITCZ, the Intertropical Convergence Zone, where it already rains a ton. But in places where it doesn't rain very much, it could get drier That's what the models are saying. And so it's all about where that increased rainfall is going to fall. And that's something we say, the richer will get richer. The rich will get richer, the poor will get poorer with respect to rainfall and precipitation. And the thing about chaos is in forecasting is, and it's particularly important for weather forecasting, is the whole idea early on that, in the 1950s when computers started coming out and we started understanding those equations and being able to put them in a computer, people thought, oh, yes, we'll be able to start with the initial conditions of what the weather is today, and we're going to be able to it's going to be a deterministic system. We're going to make a forecast to the future, and we can just forecast like we do for the tides or for, astronomical objects. But then a professor at MIT, Ed Lorenz, who happened to be a mathematician as well. If I had looked at what he was looking, I would probably have said, I made a mistake, I need to do this again. But he understood that the equations were nonlinear, and that the reason, and so he burst everybody else's bubble, because everybody else was thinking, oh, we're going to be able to make the forecast because now we have the equations. Well, there's this detail in the equations that you're still not going to be able to make a forecast past like 2 weeks. Yeah.
We got a question online.
Madeline asks, it has been reported that some areas of the Atlantic coast will face sea level rises as much as 6 feet, double the global average. Can you explain what might cause the fluctuation?
Oh, I cannot. I am so sorry.
I can.
He can, I thought so.
And so you will see variations of sea level rise across the world, not just in the North Atlantic, not just in the Southeast. Some of that's going to be driven from where that water comes from. If we have more melting from the Antarctic continent, we will actually see higher rise in sea level around sort of the Southeast and Northeast U.S. If you see more melting occurring in Greenland, it'll be in the South Atlantic. And so because of physics, because of the attraction of gravitational attraction forces, where you see that additional rise is dependent on where that water is sourced from. The double that in North Carolina, we currently have a rate of sea level rise that is almost double the global average. And that is because of local effects that lead to sea level, things like we are slowly subsiding, right? So the land mass is slowly sinking. Changes to the Gulf Stream will lead to changes in sea level. And so you have to think about the local effects that drive sea level changes in addition to what's happening globally. So, Madeline.
Thank you, Reed. The beauty of having an oceanographer at hand.
I'm having trouble understanding the linkage between global warming and severe weather events. Is that just observational, or is there proven science that shows that that's coming?
So there is some observational evidence for the past. As you have heating and you have more water in the atmosphere, these precipitating systems can become stronger and produce more rainfall, and they can also produce more rotation. And I will talk more from the side of hurricanes, for example. What makes a hurricane, the ingredients that you need are clouds and rotation. The clouds, of course, you need warm air and that has moisture in it. The air rises into the atmosphere because pressure decreases as you go up in the atmosphere. The air expands and cools, and it can become saturated with water, and you can form clouds from that. And that's how you make the cloud part of the tropical cyclone. Then it needs to spin, and the spin comes from the rotation of the Earth. So the spin doesn't change in time with climate change. What changes is how much fuel you have in the atmosphere. So you have, say, where do I start? You have the atmosphere becomes warmer. This is the positive feedback loop that intensifies hurricanes, for example. So you have more and deeper and rainier clouds because there's more moisture, more fuel in the atmosphere. So you have more release of latent heat of condensation. So as the water condenses, it releases heat. And that decreases the central pressure of the hurricane, which strengthens those pressure changes that create wind. And that strengthens the cyclonic winds, producing more rotating winds and convergence, rising air, and deeper clouds. And so the climate change relationship here would be that you're creating more and deeper, rainier clouds because with the warming of the atmosphere, there's more ability of the atmosphere to hold water. So it's easier to get the atmosphere to become saturated in rain. And that is like, it happens with hurricanes, but you can sort of generalize it to mid-latitude cyclones as well. So you could have these frontals, the frontal systems becoming stronger, and the tornadoes and the severe thunderstorms are happening where the warm air is in a mid-latitude cyclone, which is where that wind from the south, full of moisture from the ocean, for example, here in the Gulf of Mexico and the Gulf Stream is just streaming northward. And so that's happening in both types of cyclones. But most of the tornadoes that we get and severe storms, thunderstorms that we get here in the southeast U.S. are from mid-latitude cyclones.
I was surprised by the model showing that deforestation didn't contribute to climate change, because my understanding is that deforestation increases greenhouse gases, so it seems like they would be, so would reforesting will not help our planet?
That's, let's look at that figure again. Let's see what that, wait, let's go back. Where's the deforestation? Oh, land use. So, yeah, you're right. It looks like in the model it has a small effect of decreasing the temperature. I don't know why.
Scale of the events. Again, consider that the planet is 70% water. It's covered by ocean. So scale of those events of deforestation or reforestation, right? I mean, there's been significant reforestation in the northern hemisphere, which has shown for the northern hemisphere some changes in CO2 as that reforestation is taking place. But it's scale of some of these changes that you're seeing to the scale of either D or reforestation.
I know that
Everything helps, right? Those,
Yeah.
right? It's additive, right? And so it's not just this, it's not just that, right? And as that series of figures showed, it's additive, and so it's all of these things. Sorry.
Oh, I see what you mean.
One last question, and we'll try to wrap this.
Okay, so I know you mentioned the jet stream is moving, but thinking about like ice melt and warming, what happens to the Gulf Stream in these models?
Oh, any more ocean? No, it's a great question. There's something called the Atlantic Meridional Overturning Circulation. Right, Reed?
Come up with the most harmless sounding name.
Yeah,
A mock.
I don't want to take your thunder.
You don't want to take your thunder. So there is some evidence that the Gulf Stream, that this Atlantic Meridional Overturning Circulation, which includes the surface water moving as well as deep water. So you tend to have water flowing northward here where the Gulf Stream is. It sinks at the poles. and then it continues down, and that's a very slow circulation. And there's some indication that the AMOC might slow down, it may be slowing down.
I actually had this question in class today.
Oh, good.
Do any of you want to answer?
It's like eeny, meeny, miny, mo.
That's great. I mean, the Gulf Stream changes in sort of speed, volumetric motion of the Gulf Stream is pretty critical. And you look at if you look at geologic history of how the Gulf Stream and other currents across the global ocean have changed, as they've changed, you've seen significant climate variations between northern and southern hemisphere. And so they are critical to climate across this planet. The strength of the Gulf Stream is really driven by temperature gradients that we have across from south to north, north to south, whichever direction that Rosana spoke to. And so as those temperature gradients diminish from north to south, that is going to lead to changes in a lot of what we're seeing, not just in the atmosphere, but what we're seeing in the motion of that surface ocean. So things like the Gulf Stream. So that's part of that. It gets, right, so that's sort of looking at it from 30,000 feet with getting into a lot more detail. It's not quite that simple, but a significant driver for ocean currents, surface ocean currents, are those temperature gradients that Rosana spoke to. And so as those change, you're going to see changes in ocean currents. One quick one.
Will climate change create more earthquakes and volcano eruptions?
I have not seen any evidence of that.
Because I was reading about something about the weight on the ocean, the weight of the water.
Mm-hmm. And it may have something to do with what Reed was talking about with subsidence of large areas of land and that, resettling in parts. In fact, it has to do with what you mentioned also about, in the Southwest in particular, we're taking all this groundwater out of the ground and that could, and the land also settles with that. But I can't imagine a direct effect of climate change or of this warming that we're seeing on earthquakes. I can't imagine one.
Thank you. Let's give our speaker a hand. Thank you.
Thank you. Thank you all. Thank you.